Okay, so good afternoon, guys. Today we will continue our notebook homework 4 um, and finally implement attention. Um, so I believe there is a delay with computational resources because it's NSF uh, organization, and now many NSF funds are on hold, and I applied to I should apply just immediately just to Google, and in 2 weeks they should reply, and I hope we will get free GPU access. For some reason, yeah, I first tried through another. I believe for Google class it would be much easier. So, okay. Open this notebook. So today we will just code. So upload the data. Okay. So first step will be to copy paste our loss function from previous notebook. As you remember, um, we calculate this loss function after multiplying the output by the mask, because we don't want we don't care about the padding tokens. So this is the first step. So I will copy paste this from sec to sec notebook. This compute loss. Mhm. So evaluation. Also, I didn't explain last time what does it mean blue metric. So this is the metric which is used for translation, and it counts how many um, words in one sentence or in the phrase, um, let's say, so how many words that our model provided were actually in the ground truth translation. So, for example, um, let's see. here is example in Wikipedia. So for example, we have the output from model, and the reference sentence, the cat is on the map. And in this case, if we look at the blue with n equals 1, so how many one let's say one length tokens were in our translation, then we will get actually high value for this metric, because this token there was in our reference sentences. But of course, it doesn't mean that this translation is good. So that's why we include also pairs of tokens, triples of tokens, and you can increase this number. Typically, we use maximum 4 tokens. So, and here's the final formula. Is it? So it's hard to read this formula, but the idea is we count how many unigrams, how many 2 grams, 3 grams, and 4 grams were in our from our translation existed in our ground truth, and then take the so-called geometric mean. And this metric is used only for translation. Of course, it doesn't reflect the quality of translation, because it's a language and we can translate it using different words, but there is no better metric for translation. So that's why this is it's still used. It was proposed, I believe, in 2005, something like that, so, or 2001, but it's still used. Mhm. Okay, so we will copy this blue metric also from our previous notebook. But before, I want to double check the assertion if my loss function works. Mhm. Oh, we didn't define a model, okay. So let's copy. Let's see, or maybe I have this blue metric here. Let's scroll down. No, I don't. Okay, let's copy blue metric. Okay, now attention finally. Attention layer. So we will implement this formula. A token from encoder plus a token from decoder. Then we apply linear layer and activation function. And finally, we use additional linear layer to get dimension 1. And after that, we apply softmax to calculate this P. And finally, the output from attention will be the sum of all vectors in our encoder multiplied by this weights, attention weights. Okay, so what do we have here? We have, as input, we have, okay, name, I don't know what is that name. We have encoder and decoder shape, hidden shape, hidden size of, so of our LSTM. And you can play with different activation functions. Here it's hyperbolic tangent. Okay, so the first step is actually we should create some additional layers. So we should create two linear layers. One linear layer for which we will multiply by encoder concatenated with decoder, and another linear layer which will map this dimension, hidden dimension, into one. So we will create this embedding for encoder, and so we can create two linear layers, one for encoder, one for decoder, and sum them together for one and apply to the concatenation. Let's create two separate, it will be maybe more clear. So it will be a linear layer from encoder size to the hidden size. And we don't want the bias term. We will create also a linear layer for decoder. And finally, we create a linear layer, yeah, from hidden size to one that will map this to one-dimensional array of weights. Okay, so in our forward, we will calculate first logits. And logits we will calculate as follows. We will apply linear out. Okay, actually it provides the code. Okay, and that's correct, I believe. So we apply linear out. Inside, we apply activation function. And inside activation function, we take the sum of the linear layer of encoder applied to encoder plus linear layer applied to decoder. Um, and unsqueeze in dimension 1. Yes, because as you remember, from decoder, we have just one vector. Um, and encoder has multiple vectors. The encoder has shape of the input tokens. So the number of input tokens. To use broadcasting, we should make the shape of decoder vector also three-dimensional. Then it will be added to every vector in encoder. Maybe I should draw this. Um, so we have encoder. In encoder, the input is the tokenized phrase in French. Then after LSTM, or in this case, we're using GRU, we will get output vectors, and this is the input to our attention layer. Then we have decoder. In decoder, we have begin of sentence, the first input vector. And here we're using for loop, so we provide the output only one vector at a time. So that's why when we want to add this vector to every vector in our encoder, we should use broadcasting. Does it make sense? So, and after we sum these vectors together, every vector from encoder with one vector from decoder, we apply nonlinearity activation. And finally, we reduce this shape to dimension 1. And as the result, we will get just uh, the just one-dimensional numbers, and the number of these constants will be the same as the number of input tokens in encoder. So, and these numbers will be our actually attention weights. And finally, we will apply softmax. Is it clear with this line? Okay, let's move forward. Um, okay, so but we don't want to calculate attention with paddings. So that's why we should also apply mask. So let's apply mask. Um, oh, wait a second. Um, I believe I should apply mask before calculating this attention. Let's see. So in my code, I have first this activation, and then let's see. Oh no, it's correct. So okay, now let's calculate logits. We will use torch where, and if mask equals 0, we will use a small constant. So, for example, negative infinity, because log of 0 is negative infinity. Um, torch dot infinity. And here our logits, but we should squeeze. Um, yeah, I believe this is correct by dimension -1. Because um, after adding these invariants, we will get three-dimensional vector, three-dimensional tensor, batch size uh, times length and the shape um, of our embedding. But then we want to rid of the last dimension to get just batch size times the vector of weights. So that's why we squeeze. Okay, we applied mask. So it means that our weights will be zeroed for padding tokens. So when we will sum up, take the average of our embeddings with weights, the weights for padding tokens will be 0. And finally, we should apply softmax to get these normalized weights, the probabilities. And that's it. So this is how this attention layer works. And finally, attention will be just encoder times probes. Yeah, I think this is correct formula. Yep. So here we just take the weighted sum of all vectors from encoder with these probabilities. Does it make sense? And we actually should return only attention, only one vector. So the result of this layer, so the output of this layer should be just one vector of the same shape as the embedding, but it will be just the product, like probability 1 times first vector times probability 2 times the second vector, and so on. So just this weighted sum. But to visualize attention, you remember we plotted this matrix. We also will preserve probabilities, because then we will be able actually to visualize which token had high probability in during our uh, translation. So we return probes only for visualization purpose. Okay, we have implemented attention layer with so-called additive attention. If you could also use here dot product instead of this matrix, then it would be a dot product attention. Okay, so now we're ready to write the full model for translation with attention, attentive model. And then we will need to write training loop, and that's it. The rest is written for you. Okay, so what do we have here? Vocabulary size, hidden size. Okay, the AI assistant understands what actually I was going to write. So we create embedding layers for our encoder and decoder. Then um, we create, okay, it just can suggests the code that I was going to write. So then we create encoder layer, which is GRU layer. So this will be our LSTM, or recurrent neural network, that um, take as input input tokens and provide these embeddings. The second layer is decoder start. As you remember, okay, I will press tabs. As you remember, when we have the let's see. When we had sec-to-sec model, then we use the output here as the hidden state for the first token in decoder. But it's not a good idea to use this hidden vector as input to our decoder when we use attention. So in attention, we don't use this connection. So I will erase now this line because in attention, we actually, on every step of generation of new token, will look at all the tokens in encoder. And if you use as input the hidden vector from encoder, the performance of your model will be lower, worse. It's better to use as input to decoder hidden input just zeros, just a vector of zeros. So we use this in sec-to-sec model, but there is no need for this connection in attention architecture. So we will erase this one. Then we create attention layer self dot attention that we just created earlier. Um, okay. Then we create, I don't know why it still wants to create decoder start. We will need to create decoder cell. Decoder cell. So I will remove this decoder start. Decoder cell, aha. And here is an interesting thing that AI assistant suggests to use as the input size actually the sum of the embedding size and as the output from attention. And this will, and it's actually the architecture that I wanted to quote with you. So it means that after we calculate this attention vector from encoder, we will concatenate this vector with our input token into decoder. So that's why the shape will be embedding size plus hidden size. Um, okay. Then we will need a linear vector, logits, that's correct, that will be applied to the output from the decoder cell and create a vector of the size of our dictionary to get the predictions of the next token. And um, I have one more layer. Let's see if we need that. Uh-huh. Okay, in my code I have a little bit different. So um, I concatenate these tokens, but then I also apply a linear layer that maps this dimension into the original embedding dimension. Let's see if we can maybe keep it as is for now. Okay. So encode. Encode is the easiest part because in encode we just apply embedding layer to the input tokens and then recurrent neural network and return embeddings.